Good evening. This is your lecture 7 RFIC design. So we are discussing the effects of non-linearity uh, from past 2 to 3 classes, and we have looked at various effects starting from harmonics. Then we have looked at gain compression, desensitization, and in the last class we have seen cross modulation and intermodulation. And so when we discussed about intermodulation, we also understood that intermodulation products, especially the products which are coming falling very close to the desired signal, say the frequencies at 2 omega 1 minus omega 2 and 2 omega 2 minus omega 1. So those frequency components may corrupt a desired signal if a signal is present, not if a signal is present, if the interferers are there close by desired signal. The third order intermodulation terms of the interferers can in fact corrupt the desired signal. That is what we have seen in last class. And since that is a non-linearity, we also discussed about characterizing that non-linearity or characterizing the IM3 products. And for that, I defined that we will be using something called as third intercept point, IP3, which can be referred to input side as well as output side. Right. So today we'll continue. Today we'll see how we can arrive at this performance metric of third intercept point and the significance of that. We also will see a simulation how we can obtain a third intercept point or IP3 on a simulator cadence. Right. So we will start with that. So in between, if there is any issues with respect to the internet, please let me know. I do not have a third screen today, so I'll be yeah. So if I'm not responding to your post in the chat, please unmute and you can just intimate me that you have put something in the chat box. Right. So we will start with this intermodulation. We will start with this intercept point, third intercept point. Right. So I hope so far what we have discussed are clear for you guys. Right, so I'll start with this, the performance metric. Yeah, so we know that this third intercept point is basically to characterize the non-linearity of this intermodulation. And even for this, we can think about, so common method, general common method to characterize this intermodulation is to perform a two-tone test that we have done already, where we apply two pure signals, two tones of some equal amplitudes, and we'll be looking at the products at the output. So general way is actually to write a relative measure of the third order intermodulation product with respect to the fundamental term, right? So the general thing is actually to use a relative measure. We call this as relative intermodulation, relative IM. So what we do here is we will write the amplitude of the amplitude at the output of the intermodulation product, and we will normalize that to the fundamental component at the output. Where again, talking about the fundamental ideal term at the output. So I can write relative IM as the amplitude of the intermodulation term is, I hope you remember that. The IM3 term amplitude is 3 by 4 alpha 3 A1 square A2. So if it is of two tones of equal value, I can write it as 3 by 4 alpha 3 into A cube, right? So it is 3 by 4 alpha 3 into A cube. That is the amplitude of the intermodulation term to the fundamental. Fundamental is alpha 1 into A. Or this can be written as further written as 3 by 4 alpha 3 by alpha 1 into A square, right? So this is or if we are expressing this in this is relative IM, and we generally express this in 20 log. So this is written as 20 log of 3 by 4 alpha 3 by alpha 1 into a square. Right. So this is the relative Im value. But now, yeah, so this is often expressed as, we use this as DVC in order to specify that this measurement is done with respect to the carrier. Carrier in the sense, here it is the fundamental term. So DBC is decibels with respect to carrier. Right. Now, if we are trying to characterize this nonlinearity using a relative measure, the problem here is you can see that in the relative Im metric, I am totally depending on the amplitude value. So this, you can see that this is the amplitude, right? So in order to find the in order to find the intermodulation term, I'm totally depending on the amplitude of the input signal, right? Now, from a practical point of view, we always prefer, or we always should have a performance metric that should be independent of the input amplitude, because we can actually apply input amplitude and that can vary over a range. Right. So we generally will not prefer to characterize the third order, the third intercept, the intermodulation to be characterized using a relative measure or relative Im. Rather, what we go is usually for a value, for a measure or for a method where I can actually get the intermodulation component metric without independent of the amplitude. Right. So I hope you are getting what I'm trying to say here. Now here, if I'm measuring intercept point in terms of a relative measure, I'm totally depending on the input signal amplitude, and that amplitude can vary. Amplitude can be any value in the sense there should be definitely, there will be a range, but still we do not know. Or if I want to write the intermodulation value, you should definitely know the amplitude. So that is okay, but for a practical point of view, we generally will not prefer this, or we generally will not prefer to have a method which actually depends on the input level. Even if you do not know the input level, we should be able to find the IP3 or third intercept point of a circuit. That is what the idea. So so now our objective is actually to find this third intercept point. We call this as IP3, right? So our objective is actually to obtain an equation by properly understanding, obtain an equation for this intermodulation terms. So again, I assume that we are performing a two-tone test, and the fundamental signal, if I look at the fundamental component amplitude at the output, it is actually that is equal to alpha 1 into A. That is my fundamental amplitude, right? Now, if I look at the IM3 component, that is equal to 3 by 4 alpha 3 A cube. These two things I know, and I am trying to get a metric for this IM3. So what like the idea is actually to that in order to find this IP3, what we do generally is so as I increase the amplitude of the input signal, at the output your amplitude will increase A times, the fundamental component will increase in A times, but your IM3 component will increase A cube times, right? So the slope, or the increase in IM product is actually very sharp. It is proportional to A cube. Now, I hope this is also clear, that your IM3 component amplitude is relatively small compared to your fundamental term, right? Because your fundamental term is directly alpha 1 into A, where your IM3 component is 3 by 4 alpha 3 A cube. Now, if I keep on increase my A input amplitude A, I am very sure that at one specific point, your IM3 component will be equal to your input level will definitely intercept. Sorry, your IM3 component level will definitely intercept or will meet your fundamental component, right? So what I am What I'm trying to explain here is this. Let me draw graphically. So this is input amplitude, and this is output amplitude. Now the fundamental at the output is actually proportional to alpha 1 into A. And now your IM3 component will take a graph something like this. It will not go in this way. Yes, it will, this A cube value. So it will be alpha, I can write this as 3 by 4 alpha 3 into A cube. Right, this is your IM3 component. Now, as you keep on increasing your input amplitude, this your IM3 component will eventually increase. The amplitude of IM3 will increase and become equal to the fundamental at the output, right? So that is happening here. That is happening at this particular input amplitude, right? So this input level at which your fundamental component at the output equals to the IM3 component at the output. That input level is referred as intercept point 3 at input. So we call it as IIP3. Right. Similarly, if I am representing the output amplitude, I call this as OIP3, output intercept point 3. All right. I hope you understood this. Now, if I see this in a log scale. Now what you are seeing on the graph, what I have plotted now is in terms of amplitude as alpha 1a and alpha 3 by 4 alpha 3a cube. Now if I plot the same thing over a log scale, so this is a log scale, and this is also yeah, this is a log scale in fact. So on the y-axis, what I'm plotting is output amplitude. Here it is input amplitude. Right. Now, when I do this, the fundamental term will be proportional to, or I can draw it as 20 log of alpha 1 into A. It may take a shape something like this. If this is a slope is proportional to alpha 1. So I'll write this as 20 log of alpha 1 into A. It is very clear that the slope of the other curve 3 by 4 alpha 3 A cube will be much more steeper. So that that may take a graph something like this. If I plot it, it will be of this form, right? And at some point it will definitely meet. So to find that meeting point, I'm just extrapolating this, right? Meeting here, and this meeting point at the input side, we call it as, this is your 20 log of 3 by 4 alpha 3 A cube. Which one? This graph. Now this on input side, we call it as, yeah, this is, we call it is, if it is amplitude, we write it as AIIP3. Even here we write this as AIIP3. If it is at output, if it is amplitude, we write it as AOIP3. Similarly here also, this is AOIP3. Right. So I can take questions. Just give me one, or else I can actually take some questions. Yeah.
Sir, this is Anirudh, sir.
All right. Yeah.
Sir, in the numerator of the IM term, sir, relative IM,
Okay.
you've considered 3 by 4 alpha 3 AQ.
Yes.
But that refers to the amplitude of the input signal, right? A is the amplitude of the input signal
Yes.
and
Yes.
the side
Yes.
signal.
Yes.
But the intermodulation occurs because of the amplitude of some other undesirable high frequency terms, right?
Okay. I think. Okay, I'll explain that. I think you didn't get clarity on that. All right. I'm just looking at some other questions I have seen. I haven't seen the questions what you have put up till now. I'll come back to you, Anirudh.
Yes, sir.
One second. In relative IM, what is the numerator? Rakshak, the numerator. So what I am writing as relative IM is, I am writing it as a ratio of the IM3 term to the fundamental. So the numerator is IM3 term amplitude. All right. I hope that is clear. 3 by 4 alpha 3 a cube is nothing but your IM3 term amplitude. Now, is a relative IM a ratio between amplitudes of third order IM term? Yes, there is nothing called as fundamental IM term. It is a fundamental term, Sarvesh. So that is why I wrote it as 3 by 4 alpha 3 a cube by alpha 1 a. Yeah, Anirudh, your question is how we got the numerator term. So what I told is I am writing intermodulation as a relative measure. So numerator is the intermodulation term amplitude. I'll come back to that. I think a little more clarity is required in that intermodulation terms. Right. I'll come back to that, Anirudh. Yes, unmute. All right. Yes. Yes. What I have plotted, Rakshak, is both in log scale, in fact. Both the values are in log scale. Yes, yes, both input as well as output. Yes. All right. Now, coming to Anirudh question. So let me take some time just to explain this. So I don't know whether you are confused. Like I don't know how many others have the same doubt. So we explained intermodulation by considering two tones. So if I'm giving two tones, if it is a linear system, I'm expecting the same two tones with some gain, right? That is what I'm expecting. But the system is not linear. It is non-linear. If it is non-linear, we can actually characterize using a non-linear expression. That is what I have written here. Now applying this to that will result in many number of products. Some are harmonics, some are what to say, yeah, some are harmonics and some are intermodulation terms. Now coming to the intermodulation terms, so these are the intermodulation terms. So intermodulation terms, if I'm considering third order nonlinearity, it can I will get two sets of intermodulation terms. One as a result of second the square term, and one as a result of the cubic term. So that is what I have written here as IM2 and IM3. Now, when we looked at the spectrum, we understood that you can see now here this is IM2, IM3, and other terms, right? Now, if I look at different terms here, IM2s and the sum products of IM3 are little far away from the fundamental tones, right? So the fundamental tones, these two are the fundamental, and IM3 and IM2 IM3s are coming very close. Now assume that even these two tones are what we wanted, or these we are actually processing. In the beginning I told when I give these two tones as input, what I want is only what I want at the output is actually these two terms, omega 1 and omega 2. But what is happening here? Here, very close to that omega 1 and omega 2, yeah, we are getting some the two terms. Yeah, very close to omega 1 and omega 2, we are getting two other terms that we are calling this IM3 difference products. So if you look at the amplitude, IM3 terms are coming at 3 by 4 alpha 3 A1 square A2, 3 by 4 alpha 3 A2 square A1. So in this case, I am considering A1 equal to A2 equal to A, right? Because my input amplitude both are same, A1 and A2 both are same, equal to A. That means I will get IM3 product. So if I write the amplitude of this, the amplitude of this is actually 3 by 4 alpha 3 A cube. This is also 3 by 4 alpha 3 A cube. Right. Now, in order to get a performance metric, so what I wrote first is a relative IM measure. So how will I do a relative measure? I am writing the amplitude of this IM3 term, and I am writing dividing by alpha 1A. That is what this relative measure is. Right. So Anirudh, now you can unmute and ask.
Yes, sir.
Yeah.
I've got clarity now. I just had a confusion regarding the amplitude levels.
Okay. All right. Okay.
Yes. Thank you, sir.
Yeah. All right. Now, this is what we have. Yes, Rakshak, we are considering A1 equal to A2 equal to A. That is true. Now, Coming back, so we understood graphically and what we how we are arriving at this IP3 value. So to get it to get an equation or basically to determine this AIIP3, what we can do is we can actually we can equate the amplitudes of fundamental. So when I say fundamental, it is what I am expecting in the output fundamental term. So fundamental and intermodulation IM. We can equate the amplitudes of both fundamental and IM term. I'm looking at IM three terms to be very specific. So what I can write alpha 1A, that is a fundamental term. I'm just writing it as magnitude. When it is equal to 3 by 4 alpha 3 A cube, right? When these two are equal, I am calling that as AIIP3. So when it is equal, this is equal to AIIP3, right? Or to get a value for AIIP3, I can write it as under root of 4 by 3 alpha 1 by alpha 3, right? So this proves useful. This relation proves useful at least in the starting phase of the design to get an idea about the intermodulation, your IP3, the performance metric, right? Now, one more thing I want to just bring it to your notice here. So previously we wrote that a 1 dB compression point is under root of 0.145 into alpha 1 by alpha 3. This is your intermodulation, sorry, 1 dB compression point. And we can, in fact, we can arrive at a relationship between these two. So if I take ratio of AIP3 to A 1 dB compression point, the alpha 1 by alpha 3 terms will be cancelled and we will get it is close to 3.032, right? 3.032. So amplitude wise, the ratio or your IP3 amplitude is actually 3 times more than the 1 dB compression point, right? I'll just put a star mark here. Probably some of you will get doubt. Now, if I write in terms of power level, so how can I write? So IIP3, if it is power, if it is power, I'll generally use this notation as IIP3, or I can write it as PIIP3. Anything is fine. Both are used. So I will call it as IIP3, and if it is in in dBm level, I can write this as 1 dB compression point, which is in dBm, plus 9.63 dB. So what is the meaning of this? If you know the 1 dB compression point level or 1 dB compression point for a particular circuit, the IIP3 level is considered as 9.63 dB higher than your 1 dB compression point. This is actually IIP3, right? So this is the relation between these two, but it is very clear that this is something very ideal. I'll tell you why I am considering this as an ideal term. So any doubts so far from this? All right. Any other doubts? In fact, you should get few doubts here. Okay. All right. So let us solve one numerical now, and then we will come back to the discussion of this IIP3. So take down this question. Assume a Bluetooth receiver is there, which is employing an LNA, which is having a gain of 20 dB and input impedance of 50 ohms. Now the LNA senses a desired signal which is having a level of minus 80 dBm, which is at 2.410 gigahertz, and two interferers of equal levels at 2.420 gigahertz and 2.430 gigahertz. Assume that LNA is driving a 50 ohm load. Right. So the question is, there is a Bluetooth receiver which is employing an LNA. LNA is having gain of 20 dB. Input impedance is 50 ohm. Even LNA is driving a load of 50 ohms. Now, if LNA is sensing a desired signal of minus 80 dBm at frequency 2.410 gigahertz, and there are two interferers appearing subsequently at 2.420 and 2.430 gigahertz. Now, the question is, you are asked to find the value of alpha 3 that yields 1 dB compression point of minus 30 dBm. The value of alpha 3 that yields a 1 dB compression point of minus 30 dBm. That is first part. And the second part of the question is, if each interferer is 10 dB below 1 dB compression point, determine the corruption experienced by the desired signal. At LNA output. Probably this will help in understanding the concept of intermodulation itself and how the intermodulation terms are affecting your output signal amplitude, right? So you can read the question properly and you can try to figure it out. I'll discuss the answer for this, and with that we will discuss little more on IP3, and then we'll go for the simulation part. So for those who did not understand, I'll help, others can try. So the LNA is sensing a desired signal at 2.410, which is having an amplitude of minus 80. So whatever you are getting, you can actually visualize. You can draw a system and you can visualize the system. Assume that this is a Bluetooth receiver. Since it is a receiver, I'm drawing an antenna and followed by an LNA or whatever is the component given here. Now this LNA, given that the gain of this LNA is 20 dB, so this is 20 dB, and at the input we have a set of signals. One is a desired signal. So for desired signal, I'll mark in blue, which is appearing at 2.410 giga, and the amplitude is minus 80 dBm. Right. Now there are two interferers. One is appearing at maybe I'll use red color here. One is appearing at generally interferers we are considering larger amplitude than the desired signal. That is the reason why I have marked it with a larger amplitude. So this is a 2.420 giga, and one more at 2.430 giga. We do not know the amplitude level of the interferers for the time. Now the question given is, if the you are asked to find the value of alpha 3 that can yield a 1 dB compression point of minus 30 dBm. So any thoughts? If some of you got idea about this, you can in fact you can share. We can discuss and then we can solve this. I'm not asking the final answer. Instead, how to go about this?
Hello, sir.
Yes.
Maybe that the gain 20 dB corresponds to the linear gain, so we could use that to get alpha 1, and
Okay.
then P1 dB can be used to get that A1 dB, and we have that equation for relation between A1 dB, alpha 1, and alpha 3.
Okay. Okay.
So that's how we could go about the first one.
Okay.
The second one, I'm not sure yet.
All right. Okay. Yeah. It's that's true. That's correct actually. Mm, yeah. So it is correct. So second one is, yeah, I will come to the second one a little later. Yeah. So everything we have to start with the 1 dB compression. Yeah. Siddharth, your point is we can directly take.
It says that the LNA has a gain of 20 dB, so we can use that to calculate alpha 1
Yes.
maybe.
Yes. That is true. Yes.
And then alpha 1, alpha 3 are there, and from P1 dB we get
Very good.
A1
Very good.
dB, and
Yes. Yes.
that's a relation.
Yeah. True. I hope others also understood. Let me explain in this way. So the first part is yeah, alpha 1 you can take it directly. Now it is given that P1 dB, but we are familiar with the A1 dB or the amplitude levels directly. So I will just write what is P1 dB here. P1 dB is minus 30 dBm, right? So that so from this what I can get is, if I know minus 30 dBm as the power, compression point power, you should get the corresponding amplitude from that. How will I get that? I can write this, the definition for this dBm. It is 10 log of the power, the yeah, I'll write just as P to 1 milliwatt, right? So from this I'll actually get the power in watts corresponding to the 1 dB compression point of minus 30 dBm. So can I get the answer? If you are solving this, what will be the power you will be getting?
10 power minus 6.
Yes, yes, it is 1 micro. Others also can respond. Actually, you can respond in the chat box. Yes, it is 1 microwatts. Yes. So 1 microwatts. From this 1 microwatt, I know that this can be written as VRMS square by R. R is 50 ohms anyway. It is given. So from this, I need to get what is peak, V peak, or the amplitude, which is your A1 dB. What is VP? Any answers?
10 milli, sir.
Yes.
10 milli.
Yes, it is 10 milli. At 1 dB, 0.01. A1 dB. Okay, all right. Yes, it is 10 millivolt. Now I can use the formula. Now I can directly use the formula for A1 dB. What is A1 dB? A1 dB is under root of 0.145 alpha 1 by alpha 3. So here A1 dB is known. Alpha 1 is given as 20 dB, which is corresponding to 10. And alpha 3 you have to find. So this will give you the alpha 3 value, right? It is not alpha 3, mod alpha 3. Yes. What is the value you are getting? You may end up with a huge value actually.
Uh, yes, sir, it's 14.5 kilo.
Yeah.
Sir, I had a doubt regarding that. Like, is it
Yes.
possible to have alpha 3 greater than alpha 1? Because like
Uh,
alpha 1's the main one. And
so but we have to look at the even if we say it is alpha 3, you have to look at the units of that alpha 3. It is not
oh,
something we can directly compare with the gain. Gain is in
okay.
fact a dimensionless quantity, right?
Yes, sir.
Yeah. So when you so your units of alpha 3 seems to be per volt square actually.
Mm-hmm.
Yeah, so it is not that we are having a gain, like alpha 3 and alpha 1 cannot be compared directly. Another thing is, you are having, even if you have a large alpha 3, it is only 3/4 of that multiple. Yeah, maybe I cannot explain in that way. The best way is actually to understand in this form.
Oh, like because like the compression point, the value is A is some is 10 millivolts. So that's really less, like before
Less,
a
yes, yes,
huge
yes,
change
true,
comes in.
true. Yeah, and yes, that is right. That is right.
Okay, sir.
Yeah. Now, coming to the second part, yeah. So now the second part says that if each interferer is 10 dB below 1 dB compression point, that means that is actually giving a clue or giving a hint to find the level of the interferers. So 1 dB compression point is at minus 30 dBm. Now your each interferer is 10 dB below that. So what is a level of interference? It is directly I can write here as minus 40 dBm. Right. This level is minus 40 dBm. Now with that, so if I know the level or the power level of the interference which is accompanying your desired signal, then you can find the corruption of the desired signal at the output, right? So now what I'll do here is I will draw at the output. So this is your system. This is your system, and at output, yeah. So I need to know at output what are the components available. One is a 2.410, next is a 2.420, next is a 2.430. But these 2.410 and 430 are the what to say? Those are the interferers, right? Now, yeah. Now looking at the question, it is talking about the corruption experienced by the desired signal at the LNA output. So what is the meaning of that? Now when these two interferers go inside this nonlinear system, these two interferers will definitely produce the IM3 terms. These two interferers will have an IM3 term. And if you look at that IM3 term, which is one of the IM3 term, 2 omega 1 minus omega 2, or 2 omega 2 minus omega 1 will definitely appear at 2.410, right? So that is what I am going to draw now. So your input original input signal is there at 2.410, but now the condition is better. Before it was at the input it is minus 80 dBm. Now with the 20 dB of gain, now that is having a level of minus 60 dBm. I hope this is clear for you guys. Right, at input level was minus 80 dBm. Now that is getting improved because of the amplifier block in between.
Yes,
Now,
sir.
yeah, so that is at minus 60 dBm. Now there are two interferers there occurring at 2.420 and 430 with an amplitude of minus 40 dBm. Now those interferers will definitely produce one term, one intermodulation term exactly at this frequency, right? Now our intention is actually to find what is the amplitude of that interferer. So I know that that term can be theoretically written as 3 by 4 alpha 3 a cube, where what is this a? I can consider a as the amplitude of the interferer, right? So this is the term which will fall exactly at the frequency 2.410 as the intermodulation term of your interferer. So this is what I want to find. 3 by 4 alpha 3 a cube I want to find. And so when I get the value for that 3 by 4 alpha 3 a cube, then I will know how much your output signal is corrupted, whether it is corrupted fully or it is corrupted partially, or to what extent it is corrupted. Right.
Yes, sir.
Now, how to get the amplitude of the interference signal? We know that power of the interference signal is equal to minus 40 dBm. Right, from that I can find what is the amplitude of the interferer. So can you guys try that and let me know what is the amplitude of interferer? From minus 40 dBm you can get the peak value. 1 milli. It's not 1 milli, I guess. Interferer amplitude is not
10 microfarad.
No, it is not 10 micro. So what we have written as 10 micro, no, I
I
think
think
10,
it's square root of 10 micro.
yeah, should be, yes, yes. No, not even square root. So what I'm asking is, you have the power level as minus 40 dBm. What is the corresponding amplitude? Yeah, Juhi, yes, you're right. 3.16 millivolt. Yes, that is A interferer. Others can try. Only just a conversion. You can try that. Now with that, I can find what is this 3 by 4 alpha 3 A cube, and you will get it as 0.343 millivolt. Right. Now that can be converted into power. So already you have a signal here, that is a desired signal which is having an amplitude or which is having a power of minus 60 dBm. Now the interferer amplitude is also, the IM3 product of the interferer is also falling at the same frequency with an amplitude of 0.343 milli. That corresponds to some power. What is the power? Any answers for that? Nishant, can you tell me the answer for that? Nishant, are you there? Oh, Nishant is not there. Okay. Anyone else?
So what was the voltage? 342 millivolts, sir.
3.16 millivolt.
Uh,
Sorry, 343, 0.343 millivolts.
Point
Yes.
three four three. Yeah, 0.343. Okay, sir. Just
All right. So Nishant is not there, right? Nishant has logged in, but he is not available now. Aditi is there. Aditi.
Yes, sir.
Oh, okay.
I'm doing.
Yeah. All right. All right. Anand. Yeah. Very good, Anand. It is minus 59 dBm. So minus 59 dBm means it is almost. Oh, it is more than this, right? This is minus 60 and this is minus 59 dBm. That means your signal at 2.410 is fully corrupted by the intermodulation term of your interferer, right? So this is what we were looking at, or this is the problem which can cause because of the intermodulation products appearing at the output. It can, in fact, it can corrupt your desired signal. Right. So this is all about intermodulation. So today I don't think I'll get time to show the simulation. Even I need to discuss a little bit more on intermodulation. So I'll be winding up this session here, and I can take questions now. Thank you so much for joining. I can see 46 participants. All right.